Hi everyone, my name is Andrea Cracco. I'm a PhD student at my first year in the University of Verona. And today I'll be presenting a new fast tool for compacted and optionally colored construction and query of the Bruijn graphs. Let's start with a bit of motivation. As many of you already know, the Bruijn graphs are a very useful data structure that is the base of many pipelines. And as a data structure is better represented as a list of maximal unities that are the strings that are composed by collapsing the k-mers in the graph that are non-branching. And this is very useful because it allows much better compression while dealing with this type of data. Also, colored variant was proposed, and this variant is very useful for pangenomes because it allows, given a position in the graph, not only to say that it exists, but it can also map that position to from which genomes that particular k-mer came from. And a big challenge of these types of graphs is that the required amount of data that is needed is ever increasing. And for that reason, we have to focus on very fast methods to process sometimes over terabases of data. Here's a quick example and review of the time that is required to process about 1 gigabasis of genome of bacterial genomes. And as we can see, in the various years, various tools were proposed. And Bifrost in 2020 was able to reduce the needed computation time by almost 2 factors of magnitude. And today, we're presenting a new tool that is able to give another factor of magnitude of speed up. So let's start with an algorithmic overview. Typically, the Bruijn graphs are computed by a multi-stage pipeline. And for disk-based assemblers, the most common way of creating these graphs is by first doing a k-mer counting step using already existing tools like KMC3. And then with the output from these tools, use various algorithms to improve to build the final graph. But we found that this approach can be redundant since the actual k-mers and their counters are not explicitly needed, and they are not. There is no need to save them on disk just to read them immediately after and waste lots of I/O and CPU usage. So the main idea of GGCAT is to merge the algorithm used by KMC3 for k-mer counting with the first step of the Bruijn graph construction, such that we can build some intermediate data that can speed up a lot the Bruijn graph construction. So here there are some challenges to do that, because with KMC3, how works KMC3? It starts by splitting reads using minimizers, and for that reason, the reads are split in various pieces that are then put in different buckets. this has the problem that using multiple, the splitting these reads in multiple buckets divides and scatters the information needed to build the final the Bruijn graph across the different buckets on disk. And since every bucket is processed independently, there is not enough information to build again the final graph from locally available data in the buckets. Is it possible to change a bit this, the chemistry step to allow for local build of some part of the graphs that are then correct from a global point of view? The answer is yes. And the solution is to, when dividing the various reads in their contiguous runs of k-mers that share the same minimizer, to add at the end of each run a k-mer, another base that encodes a whole k-mer, that allows for that adds additional data that is sufficient to build unitics, not maximal unitics, but unitics that are still unitics in the final graph. So how does this process work? So once we have completed this step, for each bucket independently, we index all the k-mers using a simple hash map, and then we try to extend them in a quite standard way by looking at the on one end of the k-mer for all the possible k-mers that can be joined with that k-mer, that are 4. And if we find only one match, this is a potential extension for the Bruijn graph, for the unitic of the Bruijn graph. And to be sure that this extension is correct, we perform a reversal search to be sure that the k-mer that we found is not branching backwards. Once we find that there is only one extension on the left and on the right, we can we can extend by 1 the k-mer and then repeat iteratively the process until we complete. There is no more k-mers that can be extended. And then the unitics produced by this process are merged in the following phase. And this phase is also meant to be highly parallelizable, because we have these unitics with some endings that need to be merged together to build the maximal unitics. And to do that, we take randomly one of the extremities of each unitig. We compute an hash based on the extremity we chose, and then we put the whole unitig in a particular bucket that is indexed by this hash. And then, if there is another unitig with the same ending, and by chance that ending is also chosen as the candidate to be the hash of the bucket where the unitig will be put, then these two unitigs can be merged together. The probability that both of these endings are chosen in a given step is 1/4, because there is 50% chance of the first and a 50% chance of the second. And in this way, by repeating iteratively this algorithm, we come up with a correct algorithm that runs in linear expected running time. So these are the basics of working of GGCAT. And then I'll talk briefly about the technical optimizations that are present on GGCAT, since it's meant to be a ready-to-use and fast as possible tool. As I said before, all the phases of this pipeline are designed from the ground up to be very parallelizable. And then another optimization is that the intermediate working space for each sub-job that we have is kept as small as possible to allow for better caching by the CPU. And another new thing we did was to store intermediate data in a compressed form with LZ4. This could seem that a waste of CPU time, but in practice it improves a lot the I/O, and also the LZ4 algorithm is very fast, and it's especially useful for processing small bacterial genomes, for example, because there are a lot of repetitions across the various genomes. Also, another thing is an automatic optimized memory management, in the sense that the temporary files are not written to disk if there is enough RAM to keep them in memory, thus saving lots of disk I/O in computers with a lot of main memory. So now let's talk about the results. For the benchmarks, we compared the GGCAT against Cuttlefish 2 for the uncolored reconstruction, and against Bifrost for the colored reconstruction and colored querying. We tested the tools on multiple datasets, from reads from the human and gut microbiome. Then we tested it on some human genomes, Salmonella genomes. And the largest dataset we tested on was the over 600,000 bacterial genomes, with a total of more than 2.5 trillions of bases. Here are the results. When for the uncolored reconstruction from the reads, we can see that even if for human reads the results between GGCAT and Cuttlefish are comparable, for a smaller K, for larger Ks, GGCAT is clearly faster, and for the gut microbiome, for example, the difference is even greater. Then, for the uncolored reconstruction from reference genomes, these datasets fully utilize the new insights that GGCAT uses, since reference genomes are much more repetitive because they are a bunch of potentially almost identical genomes. So in this case, we can see that there is even greater speed up even for smaller K values. And for larger K values, the speed up can range from 4 to 5 times. Finally, maybe the biggest result was the comparison with the Bifrost, and so with the color reconstruction of the Bruijn graphs. As we can see, especially for bacterial genomes, the performance of GGCAT is much faster, even about 20 times faster than Bifrost. And for the largest dataset we tested on, only GGCAT was able to complete in less than 10 days, and it actually completed in less than 12 hours. Finally, I'd like to talk about the last result, about colored querying, when we compared Bifrost with GGCAT. And here we can see a huge speed up in querying, where GGCAT completed always in less than 5 minutes, while Bifrost took many hours to complete. And this test was done on 4 million short reads over the 100 human genome colored Bruijn graph that was built in the previous experiments. So the conclusions and the key points of this presentation are that GGCAT is a tool for the Bruijn graphs compacted and optionally colored reconstruction, and also for querying both colored and uncolored. It supports both raw reads and reference genomes, And with the raw reads, there is an option of putting some camera abundance cutoffs to remove sequencing errors. Then, as we have seen from the results, is a lot faster than other state-of-the-art tools. And as an additional point, it integrates the matchtigs library. That is a library that allows a more compact representation of K-mer sets. And with this new representation, with the GGCAT, it's still possible to do colored and uncolored querying on the resulting K-mer sets. Finally, the tool is written in Rust and is publicly available on this repository. And it is usable both as a standalone command line tool and as a library for both Rust and C or C++. And it's already used in a tool called Tomescu that is about a better way of indexing pangenomes. I'll spend the last few words on the future work. In the short term, we are planning to support the GFA input and output format to allow better interoperability with other pipelines and tools. And then an optional camera abundance in the final output graph to support additional analysis. For the medium and long term, we are planning to support an interoperability with KMC3 format such that GGCAT can generate KMC3 compatible outputs to be fed to the KMC3 pipeline. And then the support for, this is a more long-term project that aims to support efficient dynamic updates of the graph and also dynamic querying. Thank you for your attention. I'd like to thank my co-author, the Professor Alexandru Tomescu, my advisor, Professor Maurizzi, and then the whole Helsinki Bioinformatics Research Group. Thank you for your attention.